I have to confess that when Carlos asked me to lead this discussion, I really kind of cheated because I didn't do a lot of new slides. So we had actually a workshop that had the same name. So this came from, actually it was a good idea of Michael Flatte's. So Michael and Zeke and I have a grant together to work on, quantum aspects of cavity magnetics and other magnetics things based on VTC&E primarily, which is one of the reasons why, since, Zeke and I are both here, we're talking about this a lot. So Michael suggested, summer 2023, let's get together. I said, oh, good, you can come to Cornell and we can see waterfalls and then talk about magnons. And this presentation was one that I had been thinking a lot about, this low temperature line width question in VTC&E because it's critical for us, but it's also critical for everyone. And as Zeke said, there's just not a lot of materials that are, really low damping at very low temperature. Now, we've already heard a lot of the physics in here, and I'm going to just add some dimensions to it. But okay, so a lot of what I'm going to talk about is based on this paper from Zeke and with Dennis and Michael, adapting the, TLF or TLS, I guess I'm calling it TLSs here, from the YIG literature to VTC&E, and I'm going to talk about both YIG and VTC&E. And I have some of my own thoughts in here, and I would really love it if people shout me down. But if you do shout me down, I ask that you explain carefully your reasoning. None of this is published, so it's really like I'm not willing to stake anything, but I want to think about this the right way. All right, so I'm going to review some literature. I can't be exhaustive. I'll think a little bit. I'll expand, I'd say, a little bit on the TLS model that Dennis put together and already spoke about. I'll show some more data that is unpublished, and then and then I want to talk about it. And please stop me at any moment. All right, disclaimers. So some of you are much more expert of this topic than me. So I'm not saying this to be pedagogical for you. It's more the reverse. So this is a topic I want to know more about. And so, I had these slides. Carlos said, oh, can you lead a discussion? I'm like, great. We're just going to talk about what I want to learn about. And then whenever I say something, you guys can you can correct me and we can get it straight. And of course, I realize that many of you are experts, so please just bear with me on that. Yeah, so I think, I really feel like this is the key topic. And I made this point in my talk yesterday for those of you that were there, which is that I think line width is the critical element if we want to, and what we want to do as a community is include magnetics as an active and functional part of superconducting quantum circuits. I think it's really, really essential. And I am not at all convinced that if you want to call them quality factors or line widths or whatever, I'm not convinced that those things are kind of capped at their current value. I think we don't know a lot about YIG. We don't know a lot about VTC&E. And so what I'm trying to do here is just think a little bit about what we do know, and maybe some of you theorists are going to now run with this and figure out better ways of describing. All right, so I showed a version of this slide yesterday. I'm kind of just defining the terms the way that I want to analyze the problem, because Georg made a great point, which is that actually we care about line width, we don't care about alpha. So let's talk about line width and decompose it into what we know about it. And these may be a little bit artificial, actually. So, so we have the Gilbert damping, and alpha is phenomenological. So, if you are talking about iron, then, you can calculate, meaning, I guess, Mark Stiles, can calculate, the Gilbert damping coefficient correctly from DFT. Okay, because the mechanism, the dominant loss channel, is very obvious, which is it's polarized electron scattering at the Fermi surface. So that can be calculated. For YIG, I know of no calculation of alpha from first principles at all. For VTC, certainly not. For any other material that is a magnetic insulator, I don't know that. Okay, so, you know, Gilbert said this is the phenomenological Gilbert damping. And so that's the first thing to remember, is that it's a phenomenological damping. Like, what is it coming from in a magnetic insulator? That remains to be understood. But for the purposes of this discussion, I'm just going to say that it is phenomenological, and it's just the viscous term, which means that it's the term that depends on omega. It's the frequency dependence, okay? Then we can have other contributions to the line width. So, total line width is just the sum of the rates. So we can have magnon scattering. There is a extraordinarily large list of magnon scattering processes that involve 2 magnons, 3 magnons, 4 magnons. So, okay, fine. In the low amplitude regime, many of those are not important, but that is not universally true. That's one of the reasons, for instance, why we need our YIG spheres to be super smooth. And I talked about that a little bit yesterday. Okay, then there's inhomogeneous broadening. I would assert that this can come from materials parameters, or it can come from shape to a certain extent. If I'm talking about materials parameters, what I would think of is, let's say I have a variation spatially in the anisotropy of my sample, then different parts of the sample can come into resonance at different fields, and that's going to look like multiple modes that can exist. That's going to also dilute the coupling if it's a cavity coupling experiment, but it's going to, in a just FMR experiment, it's going to show up as broader lines. And then there's the TLS or TLF, as we've heard. I'm going to use those interchangeably, and that actually is the most sort of important part. All right. Good. Okay. You have a question.
So I had this question in my head when you showed this slide yesterday, and then I talked to a couple of people about it, and I just guess I'll just throw it out to the room. So what you've written there is a damping rate, so it's an energy loss rate. But in principle, you can also have some pure dephasing in a magnon system.
Yes.
And do you know that is always negligible? Is there some argument that allows you to just forget about it?
That's a great question. No, I don't know, but let me tell you what I do know, which is 2 things. So in electromagnetic resonators, which maybe is a bad comparison because these are spins and that's not, but just bear with me.
Okay. My argument would be that that's a very bad comparison.
Yeah, I understand. Yeah. But in electromagnetic resonators, this is sort of a negligible contribution. Right. Okay, fine. So it's essentially saying T1 is dominant, not T2, right? Now, the only actual data, so this is actually very hard to distinguish experimentally, right? And there is one and only one, I believe still unpublished example, which came from a private communication with Nakamura. And he told me that they did sort of single magnon measurements to look at dephasing, and they did the tomography, and they said, no, there's no dephasing in the YIG sphere. It's just energy relaxation. So okay. that doesn't mean that that's a universal truth.
Okay, thanks.
A very naive comment to Bill's comment. If I talk about dephasing for magnons, I mean the magnons, we have the coupling. If we have dephasing, this would basically be an inhomogeneous broadening, in my opinion, right?
Oh, let's argue with each other. I mean, it's a question of, so to some extent it's a question of terminology, but inhomogeneous broadening in my language is something that should be a static effect on the timescale of the experiment. So it's something that would lead to a random placement of your resonance frequency, for instance, that would be fixed for the duration of your measurement of the ring down of the magnetization. But a homogeneous contribution would be one that fluctuates on the time scale of your ring down. And that can still lead to pure dephasing, which would not lead to energy loss. So it wouldn't lead to a loss of magnons. It would simply turn a superposition of 0 and 1 magnons collapse it into just 0 magnons or just 1 magnon. So if you had a coherent state of magnons, it would fall into a Fuchs state on some time scale, given by the pure dephasing time. That is unpleasant.
Okay, maybe it might be an interesting philosophical discussion for later, because I mean, we're talking here about, I understand if you have local fields that fluctuate, this may change, but on the other hand, in the ferromagnets, we basically have the local conditions. And if we don't change this, we basically have different parts processing at different frequencies already. We don't have,
yeah, but so there's another way of treating that, which is to say that I have actually just more than one mode at a time. So I have some magnetic material, and there's some, like, let's say region A has anisotropy A, and region B has, and then, yes, they indeed get out of phase with each other very quickly, but I can describe that very well as just two separate modes that exist. And so then dephasing within a single mode would be then different than dephasing between two modes.
And you can remove this inhomogeneous broadening with a spin echo, but you can't if there are strong fluctuations on the time scale of your refocusing pulses.
There's no spin echo of a harmonic oscillator.
That's true. Well, that's probably true.
Actually, a student of mine and I tried to come up with a spin echo for a magnon, and we just discovered the literature that says that there's no. So. Yeah, unfortunately.
So, I mean, maybe one way you can tell the difference between a T1 and T2 processes being the cause of your ring down is your cone angle measurement, right?
Yeah, although I think what Nakamura was doing was really definitive, and at least in his experimental system, that's definitive, where he has the ability to do cavity-based tomography measurements of the magnons, and so he can do, measure in phase space individual Fock states or linear combination of Fock states and see how they evolve in time, and he just sees T1 processes and not dephasing. So, but I can't think of a better way. There might be another way, but that way is a really good way.
This situation of Yasu is a very particular one, I guess, because in order to make his experiment possible, he needs to be at a temperature which is low compared to the relevant frequency scale. So if we find a alternative scheme how to measure this as function of temperature, this might be reasonably insightful.
Yeah, so actually going back to the comment about the precession angle, that was motivating, but part of our original thinking of the precession angle was somewhat along these lines, because to distinguish between relaxation and dephasing, that's key. And in a sense, you can do it with an NV center because an NV center is a qubit. It's just that the practicalities of that measurement is challenging. So we're not sure that we can actually succeed in it. We have ideas to do it, but there's a question about the size of the signal.
So this is not a fully formed thought, but just, and it's unfortunate, I think Axel was here last week, but not now, but he has this nice paper that just came out with 2 Young spheres coupled in a resonator, and it's not necessarily the only way to make these definitions, but he did a very nice study of defining the phase of magnons in one sphere with respect to the other sphere, which allowed at least to my limited understanding, me to wrap my head around what does T1 and T2 mean for a magnon. I mean, I understand what it means for a single spin, but for a magnon, it's a little murkier in terms of a physical realization. So I don't know if that provides insight here, but if maybe thinking about measurement schemes where we're comparing two magnon ensembles to try and do these kinds of measurements and learn about damping might be a way to think our way through some of these contributions.
Did you have another question? No? Okay. All right. So I appreciated your comment, Zeke. I just didn't want to squash any further discussion. So, or shall I? All right. All right. So I want to talk a little bit about some of the experiments that people are doing. And so with this in mind, okay, keeping in mind the caveat is total line width is what we care about. Nonetheless, it's something that we want to do, which is pick apart all of these terms so that we can understand when we make samples, like where is the line width actually coming from? What do we need to do to make the line width better? I'm ignoring the TLS. I'm talking about room temperature measurements because the TLS is saturated, as we heard from Dennis earlier. So the typical thing that people do is you're then left with these three terms. You try to eliminate the magnon scattering term primarily by working at low amplitude, and two magnon scattering can be suppressed by using an out-of-plane geometry, okay, for FMR. That is, I didn't have the picture, but if you have in-plane, or it's not two magnon, it's the four magnon, whatever. We've seen it already in this meeting. If you have in the backward volume geometry, then you can get, this kind of scattering. And if you are in out of plane, then, sorry, this is, then you have omega k like this. And so under this condition, you don't have that channel anymore, right? So you can try to suppress that particular kind of magnon scattering. And then you're left with, the viscous term and the inhomogeneous term. And then I grabbed this from one of Zeke's papers because I had it handy. So, but like there's probably 10 to the 3 or 10 to the 4 papers that have a plot like this on it. So it's not like it's mysterious. But the basic idea is that you do a broadband measurement. So, you can't do this in a cavity measurement unless you put your sample in a bunch of different cavities, right? So you want to just have a broadband measurement so you can just use any frequency you want and any field you want, which is equivalent. And then essentially you measure the line width as a function of the frequency, and then you can project it back. And so the slope with frequency gives you the Gilbert damping because that's just the viscous term. And the intercept gives you, any line width that's left. If you've ignored the TLSs and you've ignored the scattering, then you're just left with inhomogeneous. And that's the standard thing that everybody's doing. And I'm just spelling it out because there's some theorists here. So all the experimentalists know this. But this is our basic way of thinking, and we're going to continue thinking this way. All right. So reviewing some other literature. So let's talk about Higgs spheres. Yeah, please. You want me to go
maybe
back?
I comment to this type of analysis. So the alpha that you extract will depend on how you do the experiment, because into the Gilbert damping, so basically this alpha summarizes all sorts of aspects, and one of the aspects is the inductive coupling to your microwave line.
Yes,
So
that's correct.
even if you then want to compare and say my alpha is the best that was ever done, then my experience tells me that you need to be careful in selecting the distance to your microwave circuit correctly, because
Yes.
otherwise you can overdamp
That's
just
right.
by coupling to this circuit.
Yeah. So for those of you that are not quite following, let me just clarify that the coupling rate to your circuit goes like omega also. And so you can get broadening from that by overcoupling. And so you want to be in a limit where you're as weakly coupled as you still have a detectable signal when you do the experiment. And if you take a sample and you plunk it on a waveguide, like some flip chip thing, that might not be the case. So especially if you have a low damping material. If you have a high damping material, actually you try to push it as close as you can. Yeah.
Quick question.
So Carlos and then Michael.
So back to Bill's comment. As far as understood, then there would be some additional term to that formula, you know, due to pure phasing, for instance. And would that maybe depend? Could it possibly depend on the frequency or in temperature as well? And then maybe this thing would be shifting like this. Maybe the temp. Yeah,
Bill?
we have to calculate this, Bill.
That's a great point. It's a great question. Do you have a quick thought to answer it?
I can say.
I can just comment that there are situations where the pure dephasing contribution does modify the spectrum that you would measure in transmission, for example. I don't know about the FMR line width at all in this case, but if I have a single qubit coupled to a cavity, if I don't include pure dephasing, then the splitting between the this anti-crossing that you measure in transmission is given just by 2G, even with relaxation, T1 processes. But if I add pure dephasing processes, that splitting changes.
Yep.
And so it's important to account for pure dephasing in that context. And I wonder if there isn't an analog here.
That's a question. Although these are intended to be weakly coupled, so there should be no avoided crossing whatsoever here. But nonetheless, it may do something that I don't know about, for sure.
Okay, I'm no expert on magnons and damping, but if I think of other systems at room temperature, or acoustic system, you can get structural damping rather than velocity damping, which means it's frequency independent. And then when you go to low temperatures, you can get all sorts of different types of damping, you know, especially with phonons, which have different frequency dependence. And so when you go to low temperature, this is what we're talking about now is room temperature, but low temperature could be very different.
And I'm going to get to that. And in fact, what you're saying is in agreement with what I'm going to say. But I think another way of interpreting that is that in general, we call this inhomogeneous. Just like we called the alpha everything viscous, we call the inhomogeneous everything frequency independent. And what, you know, the question is like, how do you decide, is it a variation in anisotropy or some homogeneous frequency independent process? And actually there are ways, but they're hard. Like we did some experiments several years ago in YIG where we did FMR imaging, where we measure the FMR like at every pixel, and then you get a spatial map of where the sample comes into resonance. And from that, you can say, well, the anisotropy here and here are different, and therefore it's this. And then whatever is left must not be dependent. So yes, but it's not an easy experiment.
I just realized I have a common question to the diagram to both of you, because you see an increase in line width for the 5 micron disks. What we observe is if we have large arrays, the irregularities between the different structures actually give you different resonance fields because you have standing spin waves, and in a single structure you may have a very small line width. Did you do any measurement on single disks? Or
Are you
only
asking
measure
me
arrays?
who?
No, I'm asking you both.
Yeah, it's Zeke that did this work.
So the short answer is no. Single disk measurements are challenging. With Greg, we took some steps to that, but I don't think that's needed to answer the question here. So first, the 5 micron disks, I think that's a growth artifact having to do with sort of the CVD sort of vortices stuff that I was talking about. So I don't think that's intrinsic. So while we didn't do a single disk measurement, we did do the filled dots. And so looking at the open triangles and the filled squares in the bottommost row, those show the same damping. So it doesn't quite answer your question, I guess. That
micron disks.
The same.
Same damping, just because you have a spread in the resonance position. That's in principle, it's a kind of inhomogeneous broadening that you can get if you have differently sized disks. You have minute variation. They all have a slightly different resonance frequency, and if you measure the array, you just get a broader line.
I think that's correct, and I mean that's I think one of the explanations.
But
the slope is the same basically.
Well, but if you just look at the intercepts there,
Yeah, the intercepts are the things that differ.
right? So, but why would we have more? I'm still kind of confused. So, what's special about the 5 micron disks?
That's what I mean.
I mean, I think you guys agree with each other basically, but Zeke's point
No,
is like there's a materials
I don't think we
thing.
do.
Well,
We can talk later.
So
I think-
we don't need to continue this.
No, just to finish this, and then we can to finish my thought. I agree with the validity of your statement. My pushback is I don't think that's what's happening here, because I don't think we would expect that kind of variation with the kind of patterning that we're doing here.
okay. Yeah, great. Okay, so I want to talk about some other experiments that people have done. Hans, I think you're on this paper, right? So you can just tell us all about it. But there's some papers from the distant past. So this is, like one of the theory papers that develops like what damping should be like as a function of temperature, and it depends on different processes that can happen. And they say these are the different processes that can happen, and then they have these different temperature dependencies, and the thought was that the dominant one should give you alpha with T dependence. And so in this work, they found that for Yig spheres of extremely high quality, if I remember reading this, the Yig sphere was like 6 nines, something like that, like ridiculous. Like, I don't know how you got your hands on those samples, but okay. And then at least down from room temperature to 100 Kelvin, the T linear behavior seems correct. There's, if you go to this kind of, also, this is just cut and paste from that paper. So, it's not mysterious, but it's the same sort of idea where you have a viscous term and an inhomogeneous term. And then if you plot the inhomogeneous term, there's some temperature dependence to it. So we've already discussed this somewhat at this conference, like the temperature dependence is possibly due to fluctuators and other things. Do you want to say more about it, since I don't want to talk about your work in front of you?
First of all, I would say that you have it kind of more present in your head than I do.
Fair enough. This was the conclusion that was stated in the paper.
Yeah, thanks. So what we tried is basically we have a technique which is called broadband ferromagnetic resonance, and at this day, so we had the impression that most of the data was acquired using single frequency experiments, and we wanted to explore if broadband approaches can add to this. And if you have access to broadband, then you can basically do a fully fledged analysis of the G factor of the system. And one has to say to this that this is a Yig sphere. But we then tested the temperature dependence, so just out of completeness. So there's a kind of predecessor of this work, which is kind of focusing on room temperature. And then we just did the full temperature dependence afterwards. And the 110 and 440, which is either in the subscripts, these refer to different Walker modes of the sphere. And so one thing that we learned is basically depending on the Walker mode that you excite in the sphere, we are more or less susceptible to surface defects. and this changed the inhomogeneous broadening. And then in the temperature dependence, you see, this is one of the main aspects of this paper, is you see that for one and the same modes, so the 110 is just the Kittel mode, where everything oscillates in the very naive phase synchronized fashion. If you look at different frequencies, then you see this peak that we have discussed about already in this workshop moving. And my take is basically, so depending on the resonance frequency where you are, you can then basically talk to different fluctuators, and they have a temperature dependence, and the old literature from the 60s suggests various mechanisms. So there's Kazuya-Lecraw, there are fast relaxers, slow relaxers, there's Orbach. And if you have the ability to look at this in a broadband plus temperature space, then you can start testing these models, and then you can try to identify what's going on. I think that would be the summary.
Yeah, I really appreciate that. Thank you. Yeah, so I think this stands as a really important, example of how to go about this analysis and what kind of information you can extract from it. All right, so I want to go a little bit deeper onto this TLS term, and this is, I'm actually showing this equation for the TLS contribution to the line width. This is the field line width. This is from, Zeke's paper with Dennis and Michael. And their analysis is very similar to, it came from the YIG one, right? So we've already heard this. I won't recapitulate it too much. It's old. So here's YIG spheres, 1959. You can see this kind of behavior, which is very similar to what, Zeke showed like 45 minutes ago. You get different temperatures for the peaks, okay? But basically it's the same sort of behavior. It matters a lot, like how the samples are polished and all of this. And broadly, I would say that when you look at this model, you have, this is the sort of core thing. You have this sort of kappa, which is some rate, and then you have this sort of thermodynamic term. And in the superconducting community, people really focus on this thermodynamic term, and you get this kind of behavior. So this is for magnons, not superconducting resonators, but superconducting resonators see the same thing, which is as you go down in probe power, at high power, you saturate the TLSs, okay? And you just scramble them all up, and so they don't contribute. It's like going to high temperature. And when you reduce the probe power, as you drive it very weakly down into the kind of minus 140 dBm for most systems is like single photon. Here it's also single magnon kinds of powers. You see this sort of increase at some point, and that's very much what people see in superconducting devices. And then, here is just showing that if you are at low power, you get this increase with temperature, and if you're at higher power, you never see the increase, okay? So you can't just make these measurements at high power and say, great. You actually have to be very careful and measure near single photon, and that's the key thing. So there's two of you, whichever one of you that want to go, please.
I just want to say we see the same thing in high Q sapphire, which is 10 billion Q. And when you go down to single photon, it goes to 10 to the 8. and the two-level system is the paramagnetic impurities. We have a paper showing that, so it's a similar thing too.
Yeah, thank you.
Yeah, I wanted to blow basically down the same horn. So with surface acoustic wave resonators, and there we learned that there is a difference between pumping these defects resonantly and saturating them, or using temperature, because when you use temperature, you can basically saturate on a much broader frequency scale compared to if you drive the system, because then you're basically only address two-level fluctuators, which are
close in energy
close
to the
and basically filtered by the mode that you are driving.
Right. Makes perfect sense. Great.
It's not a very big difference, though, is it? It's only a factor of
In this work, yeah. It's not like the
order of magnitude.
decades that you're
Yeah.
talking about. Yeah. Okay. All right. So. All right. So for YIG films, this is a very significant issue because of GGG. So. This is work from Dan Ralph's lab, collaborating with Fengyan Yang at Ohio State. And they grew a YIG film, and Dan's student, Colin Germain, measured it. And you see that what happens is the peak actually is a 600 megahertz line. And by the way, Fengyan grows great films. It's not like this is a bad film. Room temperature FMR is great in the sample. But GGG is just a disaster because it's paramagnetic like crazy. So the line width in YIG films just goes completely bonkers, and it's just, it never recovers at low temperature, essentially. It doesn't come down again. Maybe they didn't go to dilution refrigerant.
No, even that won't help you because GGG has a magnetic phase transition and it has frustrated magnetic system.
Yeah, right.
And that doesn't improve your situation.
Yeah, exactly. That was my understanding as well.
The material is great, but not in terms of line width, if you look. So this material has a line width of 4 Ørsted at 10 gigahertz, which is not so good. It has, in terms of damping, it's good, but as we discussed line width and damping, the line width of this material is not so great. So that's why I don't know what to expect at low temperatures for this.
That's a fair comment, that like the starting quality of the film really does matter, and what the chemical and defect composition is really does matter. All right, so Fengyan had an interesting idea a couple of years ago, which is just remove the GGG. Now, the usual way that you remove the GGG is like etch it off or some kind of thing, but actually he came up with a different lattice match substrate for YIG. So it's GGG, but then on top of GGG, he grew this YSAG, something analog. It's got scandium in it, whatever it is. It's not GGG, it's not paramagnetic. And so this plot, I think, tells the tale rather well. So at 300 Kelvin, everything looks the same. If you go to 2 Kelvin, GGG slope is steep. The YIG on YSAG, the slope is much better. Now, admittedly, the line widths are still pretty big, okay? But you can see that he's definitely made a significant improvement here. Yeah, Zeke.
So I'm just wondering about the mechanisms by which the magnons talk to these, especially in the GGG.
Yeah.
This would suggest that it's an exchange interaction only right at the interface. So there's really just a small number of spins right at the top of the GGG that are participating. Because this doesn't seem enough of an offset to reduce dipole coupling substantially.
That's a fair, although if you go, so this is 2 nanometers and this is 5, and they're virtually identical. Yeah. So that would suggest that, I guess. I guess the exchange would be a much stronger interaction than the dipole interaction, which would be very weak at a few nanometer standoff.
Yeah, it's just interesting to think about in terms of the number of defects that you need to have an impact.
There is, by the way, another experiment which is a bit older, where someone has actually simply removed the substrate from the YIG. These were very thick YIG films, so I think it was tens of microns, and there you could see that then the behavior changes dramatically.
Good, thank you. Yeah.
Regarding your interface remarks, we discussed about this internally for some while, and one of the hypotheses was that it basically implements some type of spin pumping where you start to interact at this interface with the spins of the GGG, and then this spin diffuses and damps the system. I'm not saying that this is the mechanism. I'm just, we talked about this as a potential problem there.
So then that would need to be a two-step process. So the spin pumping is an interfacial effect, and in principle that saturates to some extent as you start to polarize that interfacial layer with your spin pumping. But then that interfacial layer is at some different time scale through dipole coupling to other defects in the GGG, the spin is diffusing away.
Yeah, I think that's right. So the GGG is like a sink. Cool. Okay. All right. So let's go back to what is in that paper that we talked about for VTC&E. So we have the same model that we've discussed. Now I'm going to just walk through the assumptions that they made in the model. And Dennis, please jump in if I don't explain it the right way, or if you want to add nuance, please. So in this model, you know, kind of the most of the physics lies in this kappa term. And there's sort of two frequencies here. This is the kind of energy, sets the energy scale for whatever impurity level we're coupling to. And then there's this one that's a little bit separate. And I actually don't fully understand the distinction between those. But the statement was made that these are, let's just assume that they're the same. Do you have any additional thoughts on that you want to expand?
Right. So the omega int is just the exchange interaction between magnons and the two-level impurities. And with this assumption, we're essentially saying that the exchange interaction is dominating the splitting of the two-level systems.
That makes sense. Great. Thank you. All right. So then they went through this dimensionless parameterization, and I'll use it in this discussion. So you know, this just is, beta is just like the number of total impurities, and it just makes it a rate, okay? Tau is some time scale. T infinity, oh, it's been a while now. What's T infinity, Dennis? You're right here, so I'm gonna be lazy.
So T infinity is the
it's like a lattice relaxation time.
It's a lattice, but for infinite temperature.
For infinite temperature,
exactly.
Right. Yeah,
so that's the asymptotic limit of the.
That jogs my memory. Then the energy scale is 1.3 millielectron volts. That's essentially saying that you're sitting in this large exchange interaction. It doesn't actually say what the impurity is. There was some speculation that it was a defect in the VTC&E. And then essentially, because this thing is much bigger than the frequency of the experiment, which is just, you know, like gigahertz, not terahertz, you can just neglect this and just say it's that. All right. So then we have this simpler expression. And these are, you know, copied out of the paper. But one of the things that, you know, I've heard several people say that like TLS physics doesn't have frequency dependence, but actually if you just take this function and plot it, you know, there's an omega, and it does. So yeah, but okay, you've seen this plot. So let's just look at these parameters. So if you look at this tau, if you change the tau, then you can go from a really sharp peak to a broad peak that's shifted to higher temperature. If you look at the beta, and you just crank up the size of the effect basically because there's more fluctuators. And then if you have this energy barrier, the energy barrier, as we've previously discussed, kind of sets the temperature primarily. And so if it's very, very low, it's happening at very low temperature. And if it's high, it's happening at temperatures off the plot of what I did here. So I thought I'd get cute and say, all right, let's just do a you know, Taylor expansion. and try to put this in the framework of like, you know, a viscous term plus a non-viscous term. Let's just see if this yields anything useful, okay? Probably everyone else has done this too, but okay. So, so we do this. So I say, I'm gonna have some, first of all, I'm gonna say that I have some alpha prime, and it's just gonna be my real alpha, which presumably is the same as at high temperature, and then some plus whatever frequency dependence is happening in here because I've done this Taylor expansion, there's a frequency in there, okay? So then I get this kind of thing, and if I plot this, I get, you know, this very recognizable change in alpha with temperature. And under this kind of simple analysis, there can be no change in the inhomogeneous line width, okay? But if I just numerically evaluate that thing, I actually see temperature-dependent changes in alpha, and I see temperature-dependent changes in the inhomogeneous line width. So this inhomogeneous line width is, as remarked earlier, it's just coming out of numbers, so I'm not doing anything insightful here, but this inhomogeneous line width is a homogeneous inhomogeneous line width. It's a, which just is to say it's a frequency independent contribution to the line width, full stop. But I've lumped it in with what I'm calling the inhomogeneous line width all along. So I'm sorry that that's confusing. Okay, got it. So now let's compare this with some of the experiments that we have, and I'm sure I didn't get them all. This is from Feng Yan's work. This paper here from 2 years ago, where they did frequency-dependent broadband, you know, FMR at different temperatures, and they did the standard analysis. So they're decomposing it into an alpha and inhomogeneous line width, and they indeed see strong frequency dependence. And it's actually quite consistent with, you know, if you have the GGG versus if you use the YSGG, which is a substrate that is like the one that they grew, but it's a slightly different one. So it weakens the alpha blow up at low temperature that the GGG gives you. And in fact, they do see a turnaround. And interestingly, you know, they get a negative value for alpha. The line just, I mean, they show the line in the paper. It just goes the wrong way. It goes like this. Okay. So that doesn't mean that alpha is negative. I want to be clear. The line width is not negative. They're just saying, I do this analysis, and the slope is negative. Please go ahead.
I can't avoid this comment. So
Please.
if you are working in the range of 15 to 20 Ørsted at 0 frequency, and then you have something like a flat line to say I'm doing this analysis, I don't think it is correct.
But what makes you say that that's what they're doing in this experiment?
You can see that the line width is around 15 Ørsted. They're getting this negative damping at 15 Ørsted. And if you have 15 Ørsted in the YIG film, this is really crappy material.
Fair enough. So, yeah. I mean, I'm not going to argue about what's good material and what's bad material. I can just share 2 examples, which, by the way, may add to the confusion a little bit, but maybe also may add to this spin pumping idea. Okay.
So what I showed in the strong coupling experiment is actually a 700 nanometer YIG film where we left 300 nanometer GGG underneath. So there is GGG, and the damping is, or the line width is still pretty good. And we have transferred bridges away from the substrate, and we've seen line widths at 4 Kelvin of about less than 5 Ørsted. So, okay. But if you are at 15 Ørsted, I don't think it's reasonable to analyze a flat line, especially if the slope of the lines, if you look at the rest of the lines, they look different, and they're even higher than this. If you analyze the damping, so you have a difference of a few Ørsted over 10 or 20 megahertz, 10 or 20 gigahertz, and these few Ørsted already give you a damping above 10 to the minus 4, if not 10 to the minus 3. So if you do an analysis in the 10 to the minus 5 or 10 to the minus 4 range, and you have an inhomogeneous broadening of 20 or 30 Earths that I don't think that makes sense.
Yeah,
Sorry.
and just for clarity, if you read this paper, they also say they don't think this makes sense. But they have a phenomenology, or they have a methodology, and they just apply it, and then they plot the results. And there's nothing wrong with that. It's the interpretation that is important, I think. So let's just make clear that nobody believes that alpha is negative. Can we all agree that nobody believes that? Right. So it's clear, what is clear instead is that you do have line width effects where the simple decomposition into viscous and non-viscous components is not trivial. And there's something happening that we need to understand better. And it happens at these low temperatures.
So Greg, just a quick comment. We have a very flexible schedule, but today in particular we're going to have our conference dinner.
Oh yeah,
and we
we're out
have
of time.
Sylvia giving a talk at 4. So I don't want to extend the coffee break too much later. Anyway, I think we should leave the institute at around 5:30 so we can go to the hotel and take time, because then you have to go to the restaurant at so I think we can try to wrap up a little, because we can also discuss this tomorrow. Have the free afternoon, and
I am under no rush.
Yeah,
so
I'm just
we can just stop whenever. That's fine. I wasn't watching the time. Do you want to finish your comment before you?
Sure. So
go on.
So what we typically see is that in order to extract a decent Gilbert damping up, what we typically see when we want to extract a Gilbert damping is that you need to have a decent frequency bandwidth in order to make any reasonable statements.
You mean you have to go over like a few octaves?
You want to actually measure, I'm not stating 40 gigahertz, but 40 gigahertz would be nice at least. Just because that there can, I think that there are from time to time frequency dependent damping aspects that might not be covered by, or kind of might not be covered by your formula in there for low frequencies, and then it looks. So if you only look at the first 10 gigahertz, that you have this negative slope, which you would then translate into a negative alpha, and then it turns around at some point, and then you see basically the alpha, which is dominated by the proportionality to omega, and then you're in business. And one has to be aware of that this can happen, and I'm pretty sure that the authors commented this statement.
Yeah,
there.
I really appreciate that comment, actually. That's a great comment. Any other things on this slide before, I think otherwise then we're going to conclude and we can discuss if we want to go more on this. So, okay, good, thanks.
Great.